Good morning, everyone. Let's get started here this morning. So I hope midterm 1 went well for everyone, or for those who still have to take it on Thursday or Friday from alternate exams, that it goes well for you then. We'll talk more about the results of the exam once everyone's had a chance to take the test. So probably like on Monday is probably when you'll get your test results. And then later next week is when you can get a chance to review the midterm. The main takeaway from Chapter 6 into Chapter 7, I think we're going to see, is primarily just valence electrons is going to be one of the main things that we're going to think about a lot here into Chapter 7. So we'll remind you guys and talk more about that as we kind of continue into the next chapter. Kind of continuing along from Chapter 6 through 9, we're going from electron properties in Chapter 6. Now we're going to talk about how the nucleus plays a role in the properties of the atom in Chapter 7. And then get into bonding in Chapter 8, talk about the ionic and covalent bonding, get into things like Lewis structures in Chapter 8, and then start talking about the actual shapes that molecules adopt and some of the properties of molecules that result from their shapes into Chapter 9. Okay, so Chapter 7, a quick overview. In fact, we're only going to cover the first 4 sections, so we're going to cover section 7.1 to 7.4 for this chapter. And those sections include the development of the periodic table for the first section. The next section gets into what's called the effective nuclear charge. Nuclear charge is probably exactly what you would think. It's just the charge of the nucleus. It's a number of protons in the nucleus. And then the effective charge we're going to see is the charge that the outer valence electrons experience. So we'll talk about what effective nuclear charge is and how that's an important property. We're going to see that this property here is the main property that gives us the periodicity that we see for elements on the periodic table. This is going to be the main trend that's responsible for our left to right trends on how the left side elements tend to be metallic, the right side elements tend to be non-metallic, and then they range in those properties. We'll talk about size of atoms and ions in section 7.3, so we can get a sense from left to right across the periodic table what some of the trends are for size of atoms. And then we'll also talk about how removing an electron, if we take an electron away from an atom, we shrink the size of the atom, and if we have atoms absorb electrons and form anions, then the size grows. So you can get a good sense already of how ionic size compares to atomic size. And then finally, we wrap up with ionization energy, the energy corresponding to removing electrons. How much energy does it take to remove an electron? For an atom, that's always going to be positive. The electron's always attracted to the nucleus. So we have to break that attraction. So we have to absorb energy to break the attraction of an electron with the nucleus. And we'll get a sense from left to right how that energy varies. And then also we'll get a sense of how the energy corresponds to absorbing an electron, which is sometimes negative, sometimes not, depends on the element. But some atoms can more favorably absorb electrons than others. And I can probably already have you guys know which elements those are. So which group of elements do you think would have the greatest ease of absorbing an electron? So if you're looking at the alkali, alkaline, the oxygen group, halogen group, probably the halogen group, right? So the halogen group is the group that's sort of closest to filling its shell with electrons. And we're going to see that they're the elements that are most likely to have the most favorable electron affinity, the most favorable energy associated with absorbing an electron. So we can get a good feel of some of these properties already. Okay, so the first section just talks kind of briefly about the periodic table. One of the interesting things about the periodic table is that 1870-ish is roughly when the periodic table is being put together by Mendeleev. There's also, I think the book mentions a scientist named Meyer, who's also independently kind of trying to put together a table like this. And this is well before we knew about electrons, well before we knew about protons. The thing that the scientists at the time knew was a little bit about molar mass of the different elements. They knew a little bit about how to break down a substance into its constituent elements, and then they were able to figure out some properties of those elements from there. And then you can sort of see the time period of which some of these elements came to be known. So the most ancient of elements, and I don't think it's worth committing to memory which elements were discovered in which time period, just more getting a sense of probably why it would be that iron, which is relatively abundant in ore, you can sort of burn off the oxygen, be left behind with the iron that's left behind. So that was one of the first discovered elements. Copper, silver, gold, mercury. So things that are more common and easily separated from other things like tin, lead, sulfur, carbon. Those were some of the most first discovered elements. Then later we came to know the elements in the orange color, things like platinum, zinc, the phosphorus group kind of came next. And then one of the things, something that might be worth noting is what were some of the later determined elements to be discovered. Like the noble gases actually weren't known at the time of the construction of the periodic table. So getting a sense of in 1894 or later is when some of our noble gases were being discovered among some other elements. And then these really heavy elements are often not stable. And so those ones are being discovered well after the fact. So those are more recent discoveries. And then some of the really heavy elements in this range here are so short-lived, they only live for a fraction of a second. So there's really not much truly known about those elements other than you can bombard protons and neutrons and synthesize different elements. There's a section in the textbook on nuclear chemistry that talks about some of those types of reactions that go on, so it's really not something we talk a whole lot here in section 7.1. But you can get a sense that elements have been discovered, ever since ancient times on forward. And then what Mendeleev was trying to do was arrange the elements by property, and then he was trying to leave gaps where elements were not known. And so then he was able to predict certain elements that would exist that later became discovered. And so this is also well before any concept of quantum numbers, any concept of things like p orbitals, any concept that there should be 2 and 6 and 10 and 14 across for like your s, p, d, and f blocks. And so it's kind of interesting that this table is being constructed sort of well before our main concept of the atom had even emerged. And so one of the things that Moseley was able to do is you can bombard elements with electrons, and then they had a certain X-ray frequency. That X-ray frequency was proportional to the number of protons in the nucleus of the atom. And so that's kind of how the atomic number came to be known, was just from bombarding electrons looking for the X-ray frequency. And that's how different elements in the early days were discovered. Just as kind of an aside, there's an interesting show that I just saw on my TV. It said something about lessons in chemistry. Have you guys heard of this show or seen it anywhere? It's on Apple TV. It's a show about a female chemist in the 1950s making her way through life. And so 2 episodes are out. I just watched the second. It's very interesting to kind of see a glimpse of an adaptation of the past. But anyways, so effective nuclear charge is what we mentioned at the outset, was one of the main properties that gives our periodicity from left to right. So what is effective nuclear charge? And so we're told here many properties depend on the attractive force between the valence electrons, the outermost electrons, and the nucleus. And so this atom here we're looking at is sodium. So if you imagine sodium, it's element number 11. So we should have 11 electrons, 11 protons. Just getting a reminder of the atomic number tells us that the nuclear charge. So we have an 11 plus charge in this really small compact nucleus, and that charge is what's holding those electrons in place. And that's why those electrons are where they are, is because of the attraction toward that nucleus. And so from chapter 6, you can get a sense that that we would have like a 1s electron, we'd have another 1s electron in these 1s orbitals, we'd have the 2s electrons, 2 of them kind of spinning around the nucleus, and those orbitals, we then have the 2p set of electrons, and then I'll leave out the z, the third p orbital sticking straight out at us. And so you can imagine that there's negative particles that are spinning around these orbitals, and that those electrons are going to be absorbing some of the nuclear charge. And so the 11 plus nuclear charge, not all of that charge makes its way out to the outer valence electron. And so for the outer valence electron, you can wonder how much of the charge makes its way out to that outer valence electron. Our effective nuclear charge, Z is the symbol for nuclear charge. So the symbol for nuclear charge is the letter Z. So our effective nuclear charge is the nuclear charge minus whatever the screening factor is. And so this would be the effective charge is equal to the nuclear charge, and then S being the screening factor. And so the nuclear charge, this would be like the number of protons. So for sodium, that would be like 11. And then you would probably imagine the highest this screening could really be would just be however many core electrons there are in the atom. So if we're looking at sodium with the 1s2, 2s2, 2p6, 3s1 configuration, this is our core, and then this is our valence, the outermost shell. And if we get tricky for the transition metals, the unfilled d electrons, if we were to have like a lower subshell, we'd count those too. But we're not going to see that rule come into play too much here in chapter 7. So we have one valence electron here, and then we have 10 core electrons. And so the highest the screening factor can be is 10. So our Z effective is probably somewhere around +1 or in that ballpark. And we'll see in a minute how we can approximate the S factor by the number of core electrons. So it's about +1. And then we'll start to think, if you were to move to magnesium, that magnesium has the same core. So if we're picturing magnesium now with 12 protons, and now the same 10 core electrons, because it's a 3s2 configuration on top of neon. So we have the same 10 core. So our Z effective is approximately going to be 12, because we now have 12 protons in the nucleus, but minus 10 for +2. So our effective charge is going to increase from left to right for this reason, that as we go from left to right, our core is remaining constant. Like if you then go to aluminum, aluminum is a 3s2, 3p1. Aluminum has 3 valence electrons. So if you look at aluminum, 13 protons, and then minus 10 core electrons, because when we're looking at aluminum's configuration being the neon 3s2, 3p1, that these 3 are our valence electrons. So valence is the outermost shell. So the outermost shell for aluminum is the n=3 shell. So that's why all 3 of those electrons count towards the valence. And so constant core, we now have a nuclear charge approximately of +3. So I think you can see right away that from left to right, nuclear charge, the effective nuclear charge is increasing. And then what happens when you get to the noble gases? It reaches its maximum, and then when you come back to the next element down, potassium, you go back to having 1 valence electron, 19 total electrons, so 18 core. So now you go back and reset that effective charge back down to +1. So our effective charge is that trend that from left to right is increasing. Then you start over the next alkali, back down at 0 or close to +1, and you restart the trend. So the reason why the elements kind of vary in trend from metal to non-metal and then reset back to metal is probably due to this effective nuclear charge trend resetting itself each time we reset a row in the periodic table. So a lot of what I was just approximating and calculating is kind of shown on the slide here, that the effective charge is that charge experienced by the outer valence electrons. We can approximate this by taking the Z minus the number of core electrons is one way to approximate the effective nuclear charge. We'll look in a slide or two from now to try to see how good that approximation is. But again, we're showing sodium here, so we have 10 core electrons, and then the 1 valence electron. So that 1 valence electron experiences that +1 charge is the idea here. So only about a +1 unit of charge from the nucleus makes its way out to the 1 valence electron for sodium. And so you can think about the size of the orbitals is kind of shown here from chapter 6, that our 1s is roughly closer to the nucleus, easier able to absorb nuclear charge, the valence electrons then being further away, and generally in the same region of space. I mentioned this back in chapter 6. This figure here is a little confusing because this is what these contour diagrams look like for 1 electron atoms, not for multi-electron atoms. And so this figure is making it look like the 2p is smaller than the 2s, but I think you have to imagine for a multi-electron atom that has electrons in a 2s orbital, those electrons are going to repel the 2p and make the 2p orbital a little bit bigger. And so the takeaway from this figure, I think, should be that the 2s and the 2p are roughly in the same region of space as each other. And so those electrons can't really screen or shield each other that well. So, so they're going to be fighting for the nuclear charge with each other. That's why we take the core electron count and then subtract that off of the nuclear charge to come up with our way to approximate our effective nuclear charge. And so this figure, here's the one that's kind of comparing the effective charge. And so the green curve here, well, okay, let's look at the red curve first. So the red curve is the effective nuclear charge. It's calculated for the 1s shell electrons in these elements. So if you look at the 1s electrons in lithium, beryllium, boron, et cetera, on upward, this is the charge that's being experienced by the 1s electrons, and you can see that it's almost the full nuclear charge. What this is telling you is that the outer electrons, they might have a very small ability to shield the inner electrons, but just a very small ability, because you can see even for chlorine, the charge experienced by the 1s is almost the full nuclear charge. So the 1s electrons closest to the nucleus, they're experiencing the highest effective charge. The electrons further away are then going to be experiencing, for a given atom, the lowest effective nuclear charge. And so then the green curve is the approximation where Z effective is just the nuclear charge minus the number of core electrons. And so for lithium on across to neon, this is just where you're taking for lithium 3 total electrons, 3 nuclear charge of 3, minus 2 core electrons for +1, beryllium +2, boron +3, +4, +5, 6, 7, all the way up to +8 for neon, for that constant increase in effective nuclear charge from left to right. And then we reset ourselves back for sodium, back to +1, back to +2 for magnesium, +3 for aluminum on upward. So the green curve is just kind of showing you what the trend looks like for the effective nuclear charge being approximated by Z minus the number of core electrons. And then the blue and the yellow curves are showing you some more advanced methods for calculating effective charge that take into account a very small ability of the valence electrons to screen each other. And then also one of the curves, the yellow curve, is showing you some more advanced computational methods that can calculate effective charge. And what you see is the same trend. So you see that the Z minus the number of core electrons isn't exactly correct numerically, but we get the same trend if you use a more advanced method to calculate the effective charge. And so the trend that we can see is that the effective nuclear charge increases from left to right, that there's no break in the trend. There's no elements from left to right that are breaking this general trend of increase of effective charge from left to right. And then we reset the effective charge when we reset the next row of elements, leading to the periodic nature of our elements. And so our core electrons screen each other most effectively from nuclear charge. The valence electrons can maybe screen each other a little bit, but not very effectively. And then the core electrons, one thing that's maybe a little hard, maybe I'll erase here. If we can compare, so with the green curve for lithium to sodium, they're both +1 because it's either 3 minus 2 or 11 minus 10. But if you look at the more advanced methods, you can see a little bit of an increase. Maybe it's actually a fairly substantial increase for lithium to sodium, that you actually get a little bit of an increase when you get to sodium compared to lithium. If we were to look at potassium, even a little bit more pronounced, that our effective charge, when we reset itself each time down, is going a little bit higher. And so we'll summarize that on the next slide here. So the effective nuclear charge increases, we would generally say, greatly from left to right. This is where we're getting our big trend differences. This is where we're going on the left side from being a metal, the right side to a non-metal. So big changes in properties of the atom as you go from left to right from this increase in effective charge due to the screening ability primarily of those core electrons. And then we get a slight increase down the column in effective nuclear charge. Now, when you're looking at this slight increase from like here to here, that slight increase never really changes the property of the atom. You know, in terms of lithium to cesium, we stay metal, we stay solid. We're not really greatly changing the property of the atom, like we're going from solid to gas from left to right across a row of the periodic table. So we get a slight increase in effective nuclear charge down a column. And the reason or the explanation for this is as you go from having a 1s core to a 1s, 2s, 2p core, to then a 1s, 2s, 2p, 3s, 3p core, those core electrons are getting further away from the nucleus. Their screening ability becomes a little bit poorer. So screening ability becomes poorer as those core electrons are becoming more diffuse. So as you go from top down, the core is becoming bigger, not screening as well, and the effective charge goes up a little bit. Okay, so sometimes these questions here are so easy because we just talked about it, so sometimes a question like this might have been better, or we might want to make sure to take a quiz on this sort of topic a day or two from now to make sure this kind of sets in. But as we're thinking for effective nuclear charge from left to right, let's just try to make sure that for fluorine versus iodine, we're using that top to bottom trend. So for F versus I, we're thinking, how does from top to bottom effective nuclear charge vary? And then from left to right, how does it vary? So when you guys take a minute or two on this question here, feel free to compare with your neighbor. So again, we just went over the rule in the previous slide, so maybe it's too fresh in our memory, but from top to bottom, we get a slight increase in effective charge, so iodine would have the higher effective charge, and then chlorine from left to right, we get that great increase from left to right, so chlorine should have a lot higher of an effective charge compared to sodium in the same row, and so we'd be looking here. And so now we can already start to sort of forecast some of our other trends. If you think about sodium versus chlorine, so sodium, they're in the same row as each other, well, yeah, in the same row of the periodic table. Sodium, low effective charge, chlorine, high effective charge. So you can sort of get a sense that chlorine's probably going to be a lot smaller as a result of this increase in charge. Those electrons are going to be that much more attracted to the nucleus. So we might start to expect that chlorine's probably going to be smaller. You can probably already expect something we already know, that sodium is going to be more likely to go to plus than chlorine. So that one electron, bigger, weaker charge holding onto it, probably easier to break that electron off of sodium to go to sodium plus. Chlorine, those electrons really close to the nucleus. It's going to be really hard to remove an electron from chlorine. We can probably already get a sense that the ionization energy trend is going to kind of coincide with this effective charge trend. The top to bottom size trend maybe gets a little confusing, probably less to do with the effective charge, it's more to do with more electrons. So iodine's going to be bigger, fluorine's going to be smaller. But we'll be talking about that as we continue into the topic. So the next topic here in the chapter is the size of atoms. And so a little confusing part of the size of atoms is, on one hand, you might want to know the non-bonding radius. So if you had the atom where it wasn't bonded to something else, which is kind of a problem because hydrogen rarely exists just as H atom. It's just not stable enough. So if hydrogen exists, it bumps into another H atom, it exists as H2. So for something like hydrogen, we're probably more likely going to be talking about its bonding radius, the size of the atom when it forms a bond with some other atom like itself, or the same thing like oxygen forming like a double bond. We might have the fact that oxygen forms like a double bond. So when we think of oxygen, we might wonder if we see a size of O atom having a certain radius, we might want to wonder, is that the non-bonding radius? Or if we make a bond, the radius is going to appear smaller because the atoms get closer together due to the sharing of electrons. So the non-bonding radius is sometimes called the van der Waals radius. It's half of the shortest distance separating two nuclei during a collision, which is actually hard to imagine, but it's just if you could have maybe two helium atoms that aren't going to bond together if they bump into each other, then you can more easily calculate one of these non-bonding van der Waals radii. But hydrogen's pretty hard because if hydrogen bumps into itself, it's going to shorten its bond and connect together. And so then the bonding radius is half the distance that's separating the two nuclei in the atom. So if you just take the bond distance d, cut it in half, then that would be the bonding radius of each of the atoms, say for hydrogen. So the idea here is if this is the non-bonding radius, then the bonding radius is going to be shorter due to the overlapping or the sharing of electrons between the two atoms. And so the bonding radius is always going to be shorter than the non-bonding radius. So the bonding atomic radius shorter than the non-bonding radius, just due to sharing of electrons. Now, bonds can't be infinitely close together. They can't perfectly overlap, right? Because the nuclei have positive charges. Those charges repel each other. The electrons have a charge too. They don't want to get infinitely close together either. So bonds have some ideal bond length where the protons and the electrons kind of reach a happy medium point. And so we'll even see that with ions, that if you have a plus and a minus ion, that they have a certain distance they like to get from each other. That sort of maximizes the attraction and then minimizes those repulsive forces that the nuclei will start to have with each other. Now, I think the reason why we talk about bonding atomic radius on the previous slide is when we see a chart like this, that we can imagine that these are not the non-bonding radii, but the bonding radius. And so the bonding atomic radii are shown for elements below in the periodic table. And then the bonding atomic radius here is assuming single bonds. And this is something that's kind of hard to, well, it's hard to write. Single bonds. Like oxygen, for example, will bond with a double bond with itself, but then when it bonds with something like hydrogen to make water, it's single bonds. And so if you want to come up for a chart that relates to the size of oxygen, this chart here is just looking at oxygen size when it single bonds with other atoms. We'd have to look up a different radius for oxygen when it forms a double bond, or if it forms a triple bond with something would be even smaller. And so this chart here is really useful for comparing size of atoms when they're all forming single bonds with each other. Now, we're at a point in the course where we don't really know how to predict whether a molecule has single versus double versus triple bonds. We'll see that when we get into chapter 8. So I wouldn't worry too much about the nature of the bonding in a molecule, other than this chart here is just looking at single bonded atoms and their relative sizes so that we can get a sense of the size of atoms from left to right. And then we also see a weird trend emerge for the noble gases, which don't bond with anything. So when we look at the noble gases, because they don't really form covalent bonds with other atoms because of their nature being stable as monoatomic gases, when we look at the size, see how the size decreases towards fluorine from left to right across the first main row. And even we get the decrease from hydrogen to helium. But then for the noble gases, see how it goes up in size? But that's kind of a nuanced trend. That's what I would call not something that's really real per se, because that's just showing us that the bonding radius of fluorine goes smaller. The non-bonding radius of fluorine would certainly be bigger, and then the non-bonding radius of neon would coincide with being smaller than fluorine. So we really should have expected a decrease from left to right without the noble gases breaking the trend. But when the noble gases break the trend, we just go back to, oh, okay, for lithium, beryllium, on across the fluorine, these are bonding atomic radii, which go shorter than their non-bonding radius, and then the noble gases here are showing us the non-bonding atomic radii, just because they don't form bonds. So you can't really mimic the bonding atomic radius for the noble gases. So the noble gases appear bigger, but that's a nuance of the trend of what it is that we're showing you the size of here, where all the other atoms are showing you that shorter bonding atomic radius. But we get the left to right decrease in size, and that would be best explained through the effective charge. So as you go from lithium +1, beryllium +2, increasing that effective charge is pulling those electrons in more closely. So positive attractive force between the negative electron and that positive charge is what's dictating our size here. So we get a decrease in size as our Z effective is increasing with that same trend. And then when we go from top to bottom, it really doesn't have anything to do with the effective charge trend. That was a slight increase from top to bottom, but it has more to do with just the increase in number of electrons. So we're just going from a core of 2 for lithium, a core of 10, a core of 18. So you're growing the core size, which is growing more diffuse, more electron repulsion, so more electrons, bigger size. And so we get an increase from top to bottom as our valence orbital size is increasing. Our core electrons become more diffuse from top to bottom. And so the top to bottom trend, notice how it's very consistent increase from top to bottom, and that there's no break in that trend. Okay, now when we look across the transition metals, I don't want to worry a whole lot about the transition metals. In fact, I don't think we tend to talk too much, but notice how we do see generally the trend, and then you get a little bit of break in the trend towards the end of the transition metals. We're not going to dwell much on the transition metals, but I just wanted to mention that the elements kind of are following the rules, but this has a little bit to do with the configuration of the atoms, but we're not going to dwell too much and talk too much about the transition metals. So this slide here is showing us the size of cations versus anions for some of the elements in the periodic table. Let's zoom in a little bit. And so look at lithium size, 1.28 angstrom. Lithium plus, taking that one valence electron away, goes to 0.9 angstrom. Notice that we get a decrease in size. Beryllium to beryllium 2 plus. The most common ion for a given element will be stripping away all of its valence electrons, so beryllium 2 plus grows a lot smaller than beryllium. Notice the same trend for boron 3 plus. The trend continues for sodium to sodium plus. Sodium plus is smaller. This makes perfect sense, right? We went from having, for sodium, a 3s1 core on top of neon. Get rid of the 3s1 core, the atom becomes a lot smaller. And so cations are smaller than their parent atoms. So sodium plus is smaller than sodium. Magnesium 2 plus is smaller than magnesium. So continuing the trend here. And so there's no break in this trend, that you take away the valence electrons, the atom becomes smaller. And so what's going on is you're getting rid of electron repulsion on top of just removing the electrons that were taking up space in those larger orbitals. And so then now adding electrons has the opposite effect. If we go from O to O2 minus or from F to F minus, notice that our size is increasing. And again, this probably doesn't seem too unreasonable, because what we're doing for oxygen is we're going from oxygen being a 2s2 to a 2s2 2p4 to an O2 minus to a 2s2 2p6 configuration. And so we're adding 2 more electrons, and then those electrons cause the other electrons to be repulsed. They have repulsive forces because they have the same charge, they repel each other. And so the greatest reason we have the increase in size from O to O2 minus or F to F minus is electron repulsion. And so our anions are larger than their parent atoms due to electron repulsion. So those electrons that we're adding are repelling each other, and then that serves to increase the size of the ion. So F minus is bigger than F, O2 minus is bigger than O. Now, an interesting question would emerge, and that might be for the size of like sodium versus fluorine. So, and this might be on the next slide too, but think about the size of sodium versus fluorine without maybe looking at the chart in terms of a prediction. And so for sodium, sodium's bigger than lithium, right? Because it's further down the chart. And then lithium is bigger than fluorine, right? So if you're thinking of sodium, you're thinking it's bigger than lithium, lithium's bigger than fluorine, so sodium has to be bigger than fluorine, right? And so we can double check the chart. In terms of the size of sodium, sodium is 1.6 angstroms in radius, and then fluorine is 0.57. It's like not even close. Fluorine's a lot smaller. Okay, so that's good. Now what about this trend here? What about sodium plus versus F minus? What if we strip that electron off of sodium plus? And what if we absorb an electron onto F minus? Which one's bigger? Do we keep the same trend? Like, is it still sodium plus bigger than F minus? It's actually not going to be the case. So let's think about this for a minute. We have 10 electrons for sodium, because we had 11, we took one away. And then fluorine had 9, we added 1, we have 10 electrons here as well. So these atoms here have the exact same electron configuration. That's called isoelectronic, is a fancy word for that. So these can be said to be isoelectronic. I think this is on the next slide in terms of a word. That just means same electron configuration. So they're both 1s2, 2s2, 2p6s. And so then if you're sodium, or if you're fluoride, which one do you think is going to be smaller? If you have an 11 plus charge to hold 10 electrons in versus a 9 plus charge. So the difference here is you have an 11 plus versus a 9 plus charge to hold the exact same count of electrons into place. You would probably expect having more protons is going to pull those same kind of electrons in more closely. And that's exactly what happens. So if we double check our chart here, sodium plus 1.16 angstrom, fluoride 1.19 angstrom. So fluoride's not much bigger, but it is bigger. So fluoride goes bigger than sodium plus, despite the fact that fluorine with a neutral charge is a lot smaller than sodium with a neutral charge. And so what this boils down to is when we're comparing atoms without charge, we're comparing just the size of elements and their neutral charges, then we're using our atomic trends from left to right. That size decreases left to right, increases top to bottom. And then whenever we're comparing ions, we have to do a little bit of thinking. And so the thinking might be, do we have one of these isoelectronic series? And so when we're comparing O2 minus to F minus to sodium plus to magnesium 2 plus to aluminum 3 plus, that we have to compare and look at the protons. So we go from 8 protons in oxide to 9 in fluoride to 11, 12, 13 in sodium, magnesium, aluminum. Look at how aluminum, how much smaller it is due to having still 10 electrons, but that 13 plus charge to pull those electrons in, a lot smaller. Magnesium grows bigger, sodium bigger, fluoride bigger, oxide the biggest of the 5 on the chart. I don't want to flip back because it makes the video screw up, but neon, can somebody look back in the notes? What's the size of neon? Okay, so the previous slide must have been showing us the diameters, not the radii. The bonding atomic radii chart was showing us the radius. So neon, I get 1.16. And so it's oddly the exact size of sodium plus. Not entirely sure why it wouldn't have been. Like, it would be perfect if it were like 1.17 or 1.18, but it could be some rounding errors here too. But you can kind of see that neon's kind of falling right in the middle where we would probably expect it between sodium plus and fluoride because it has now just 10 protons. Okay, so I just wanted to squeeze back in the concept of the noble gas size really is the size you would expect if you were comparing the sort of non-bonding atomic radii trends for all the atoms. Okay, so ions, cations are smaller than their neutral counterparts, anions are bigger than the neutral counterparts, such that we're comparing isoelectronic when the number of electrons are equal. We're just looking at the protons to guide us in terms of which of the ions is bigger. Again, probably too easy to do this question. Let's do this one together instead of me throwing this to you guys. But sodium versus fluorine, this comes back to the bonding atomic radii trend. And that's just the simple left to right decrease in size, top to bottom, increase in size. Just so that we know what trend it is that we're using and why we're using it. So both the atoms neutral, then we're using our normal bonding atomic radii trend. And so here, this is that trend that sodium bigger than lithium, bigger than fluorine. And so sodium has to be bigger than fluorine. Now, I make the trend through lithium just because it makes it clear why sodium has to be bigger than fluorine. Sometimes when you're comparing two atoms in two different rows, it's a little bit hard to compare. If we flipped this problem and said, like lithium versus chlorine, do you see how that's a tricky problem, maybe not answerable, just based on the trend? So lithium, if we compare the wrong trend, go against the trend, sometimes it's hard to compare and know which one's bigger. So you can only compare atoms if there's like maybe an atom in common with them where you can make the trend like lithium for sodium and fluorine. Sodium plus is sodium versus sodium is that the cation is smaller than sodium. F minus now is bigger than F due to gaining electrons. And then F minus bigger than sodium plus just due to the isoelectronic series. Now, it doesn't, like, what if we were comparing the size of sodium plus versus F plus? if we were comparing the size of atoms with the same charge as each other, well, then I think we just go back to this should follow the same trend as when they were neutral, I think. Shouldn't have done this example on the fly, but it would be interesting to see and compare. But I think that trend should generally hold up, that if you're comparing two atoms that have the same charges, it would just be like if they both were neutral. So this would just come back to the same trend that sodium plus should be bigger than lithium plus, which should definitely be true, and that lithium plus, I think, should still be bigger than F plus. So that sodium plus would still be bigger than F. So we're just coming back to the same bonding atomic radii trends anytime the two atoms have the same charge as each other. And so the trend here, you use the isoelectronic because they both have 10 electrons. So the moment they share the electron count is when we're comparing protons. Probably too easy, but take a minute or two. I hope this is easy. In my head, I'm like, this would, again, be better in a quiz tonight or tomorrow night, so you get a little bit away from the material, force yourself to recall it. But just let's make sure that you guys can take a minute or two and agree that these are pretty straightforward to come up with the atom or ion in each pair that's the smallest. So K versus Cl, what do you guys have for the smaller one? This would be chlorine, right? So just like before, potassium is going to be bigger than sodium. Sodium has to be bigger than chlorine. So chlorine has to be the smaller one of the two. And then K plus to Cl minus. K plus, potassium has 19. K plus would have 18 electrons. And then chlorine has 17, so chloride would have 18. So they both have 18 electrons, isoelectronic, more protons, 19 plus versus 17 plus, so the smaller one here is going to be K plus. So chlorine and K plus would be the smallest members of each of those pairs. Okay, so ionization energy does follow the same trend we would probably expect. So like if we're going from left to right, we have this increase in effective charge, decrease in size. Both of those are in favor of increasing ionization energy. So ionization energy, this is really going to be related to the energy of electrostatic attraction. Remember this kappa Q1, Q2 divided by D. So if you can increase the magnitudes of charge, one of those should be 2, Q1, Q2 divided by D. So one of those is the charge of the electron. The other one's the nuclear charge. If you increase the effective charge, you're going to increase the magnitude of attractive force between the electron and the nucleus. And then if you decrease the size, so if you decrease the size of the atom, you're putting that negative electron closer to that higher charge, which also increases that energy of attractive force. So the attractive force of the negative and the plus. So if you remember here, the negative and the plus are where we get the attractive force. We're going to get the strongest attractive force when that nuclear charge is the highest and when the electron is the closest as it can possibly be to the nucleus. And so then our effective charge, or excuse me, our ionization energy should be increasing as we go from left to right because the electron's closer to the nucleus and the nucleus has a higher charge, harder to separate. And so the left to right trend is if we look from top to bottom in this chart, is the left to right trend for sodium on across to the noble gas. Sodium is about 500 kJs per mole to remove 1 electron from sodium. And then for argon, it's about triple. It's about 1,500 kJs per mole to remove 1 electron. So the ionization energy is the minimum energy required to remove an electron from the ground state of the gaseous atom or ion. Now, the fact that we're saying gaseous atom might be a little confusing because We're talking about removing an electron from a gaseous sodium versus a gaseous magnesium. And the reason why we're going to specify a gas is because we want to have like a constant comparison. We don't want to compare the ionization energy from a metal, which maybe being in a metal form would change the ionization energy compared to the non-metallic elements being in a gas. So we just determined we'll just make them all gases. So we're taking the ionization energies, the energy to remove an electron from the gaseous atom. And then the first ionization energy is the energy to remove that first electron. So that would be like sodium gas going to sodium plus, still as a gas, plus the electron removed. And so the energy for that step, like the delta H of that reaction, would correspond to the I1 or the IE1. I like the IE term instead of I1, but the book says just I1, I2 for the first ionization versus the second ionization. So the second ionization energy, the IE2, or the I2, is the energy required to remove the second electron and just the second electron. So the I2 of sodium would look like sodium gas with a positive charge because we've already removed the first electron. And so this then goes to sodium plus 2, still as a gas, and then plus that second electron coming off. This corresponds to IE2. And so look at the magnitude of IE2 for sodium. It's a lot higher. It's almost 5,000 kJs per mole. So it takes about 500 kJs per mole to remove the first electron from sodium, then almost a factor of 10 more to remove the second electron. Why might that be? Well, for sodium, we have that 1s2, 2s2, 3s1 configuration. The first electron is that big 3s1. Now we have to remove one of those small core electrons that's now experiencing a really high effective charge. This is like removing an electron from neon if neon had an extra proton, if you think about it. So it's like give neon another proton, and then that kind of makes it the sodium atom then, and then try to remove an electron. And so that should take a lot of energy, and it does take a lot of energy. And so whenever we start removing core electrons, you see a big increase in the ionization energy. So each successive ionization is always greater than the previous. Like if you go from magnesium, look at its I1, 700 kJs per mole, higher than sodium, because for magnesium, effective size is smaller, effective charge is higher, harder to remove the electron. And then if you look at the second ionization, even higher, it's always going to be, if we strip one electron off of magnesium, what do we do with the one electron left over? We make it a little closer to the nucleus, it has less repulsion, and so harder to remove the second electron off of magnesium. One of the confusing things, since it's about double, sometimes students misconceive that the I2 is the total energy to remove both electrons, but it's just the energy to remove the second electron. So to go from magnesium to magnesium 2 plus would take 738 plus 1451 kJs per mole of energy. So about 2,000 kJs per mole to go to magnesium 2 plus. Now, if we want to try to remove that third electron to go to magnesium 3 plus, bad idea, right? Because now we're removing a core electron that has a huge increase of energy. It takes 7,000 plus kJs per mole to remove a core electron from a magnesium atom. And then you could look for aluminum. Has a weird trend. We'll talk about that a little bit later. The left to right trend's a little bit nuanced because as you go from 2s, the 2p subshell is higher in energy. So as you go to aluminum, you're removing an electron from a 2p subshell. It takes a little bit less energy to remove that electron. And then when you go to the next 2p subshell for silicon, it increases as you would expect. Then we get an increase to phosphorus as you would expect. And then we get a slight decrease down to sulfur because now sulfur has a spin paired electron, which kind of like leads to some electron repulsion that we're freeing up. So we get a little bit of an inconsistency from left to right when you look at ionization energy, in that we don't get a increase all the time from left to right, but we get a little bit of a periodic inconsistency. But we'll look at that in a minute. And so, but if you go from the I1 to the 2 to the 3 to the 4, for every time you increase another electron being removed from an atom, it takes even more energy. So each successive electron takes more energy than the previous electron. And then whenever you get to the core electron, look at the core electron for phosphorus being removed, that it goes from 6,000 from its last valence electron to 21,000 for its first core electron. So core electron removal, a lot of energy is required. Okay, so this trend here is going to show us that that left to right trend, that inconsistency. So from left to right, we get the increase in, from left to right, ionization energy increases, but with a periodic inconsistency. So we get an increase, then we get a decrease, then increase, decrease, increase. And then we see that trend repeat itself: increase, slight decrease, increase, decrease, increase. So the decreasing columns are the NP1 configuration and then the NP4 configuration, being a little lower than what we expect. And this just comes back to another anomaly, or another, like when we're looking at the noble gases breaking from what looked like the bonding atomic radius trend, but it really just had to do with they didn't bond. So they had a good reason for breaking the trend. Ionization energy here is a little bit more complicated than maybe what we're making it seem. If we're thinking from left to right, we get the decrease in size, increase in effective charge, but we have different orbitals being involved. And so a 2p orbital is generally a little bigger than an s orbital. So the first time we have a p orbital, we're just removing an electron from a different type of orbital that's now a little bit bigger, a little bit easier to remove the electron from, therefore a little bit lower in ionization energy. If we could ask a weird question, or if you could go into like a spectroscopy that would allow you to see for something like boron, if you were to remove an electron from its 2s orbital instead of the 2p orbital, that 2s electron takes more energy than for the preceding atom of beryllium. So if you're going from left to right, saying if we just remove the electron from the same orbital, then you get the exact trend you expect. So if you look at the removal of a 2s electron from left to right, you get an increase in that ionization energy from left to right. It's just, as soon as we're moving from a p orbital instead of an s orbital, it appears to have a lower ionization energy due to that configuration anomaly. And then we have a spin pairing phenomenon, where we're like, it took energy to spin pair the electrons that we get back when we free up the electron and remove the electron from the NP4 configuration. So that's why the NP4 is lower a little bit, so it's a configuration anomaly there as well. But then we continue the trend because from oxygen to fluorine to neon, while we're spin pairing the electron still, we're making that spin pair electron closer to the nucleus with a higher charge. So we go back to increasing as we would expect. So a little bit of a nuance from left to right, but general increase in ionization energy from left to right. And then our top to bottom trend is that our ionization energy you can actually look at the trend. Let's examine it real quick. We get mainly a decrease in ionization energy from top to bottom. We have a few cases, like in the lead goes up. So in not every case do we get a decrease in ionization energy, but generally a decrease in ionization energy from top to bottom. And why might this be the case? Well, we have two counter-opposing trends again. So the counter-opposing trend would be from top to bottom, the size is increasing. So the valence shell is moving further away from the nucleus, which that would make you think easier to remove the electron, but the effective charge goes up by a little bit, which would make you think harder to remove. So we have a counter-opposing trend when we think of the energy of electrostatic attraction. So what happens when the charge goes up a little bit, but the distance goes up? Which one wins out? Usually it's the size that wins out. You can see that for most of the elements, the size trend wins out. So generally from top to bottom, we get the decrease in ionization energy due to the increase in the size of the atom and how that plays a role in the electrostatic attraction of the electron to the nucleus, despite that slight increase in effective charge. You can see a couple cases where, in fact, all these elements here are kind of breaking the trend of size, and that's only explained by the effective charge trend dominating for those atoms. And so we can understand and comprehend or get a sense that it's just negative, positive attractive forces versus their relative sizes in terms of the trends for ionization energy. Okay, we are just about through. We're not going to look at this question today, but we have to talk about configurations of cations, get into electron affinities. I'll throw a couple review problems in for I'll put up like a little review packet that we'll look at on Friday, and then we'll probably get into a little bit of chapter 8 on Friday to get this start on our next chapter. Okay, so thanks for coming to class today, and I'll see you guys on Friday.